Let's talk about a few special sets that will come in handy in probability theory. The first of these sets is the empty set. This set is a set that contains no elements. There are no objects within this set. So as of now, we've only looked at sets that contain at least one object. And this is the first time we actually have a set that contains no objects. So how does this look like? We denote the empty set by a special symbol, which looks like this. And in set notation, it's just going to have an open brace and a closed brace. And within this set, there are no elements, no objects, no objects or elements in the empty set. In probability theory, this set comes in of great importance, especially when building it up. So right now it may not seem so important, a little ambiguous, but all you have to know about the empty set right now is that it's a set that contains no objects, no elements. Maybe a description will help, an example. Um, Imagine we want the set of all the iPhones that came out in the years 1920 to 1980. Well, that set of all the iPhones that came out between 1920 and 1980 will be empty because iPhone only came out, I believe, when was it? 2004, 2005. Um, so that type of set will be empty. So it kind of makes sense to have a set like this to describe a collection of objects that just aren't there. Okay, so that's the empty set. The next set I want to talk about is the set of natural numbers. Natural numbers is going to be denoted by a bold-faced N, and it's the set that contains the element 1 and every number you get from adding 1 to the previous number. So the next number will be 2, then adding 1 to 2 you get 3, and then 4, and then 5, 6, and you could go on up to positive infinity just by adding 1 to the previous number that you get. And this is the set of natural numbers. I guess they're called natural because you could start off by counting these numbers on your fingers, right? 1, 2, 3, 4, 5, 6, 7, up to 10, up to 20 if you're counting your toes, but we don't have infinitely many fingers, so I just like to think of the natural numbers as a set containing the element 1, and then we add 1 to it, and then we add 1 to the previous number that we get. Some textbooks actually start the natural number set off with the number 0. This difference isn't so important to us, so we can just start off with the number 1. The next set is the set of integers. This set is denoted by a bold-faced Z, and it's going to be the set that will contain the numbers that are actually in the natural number set, including the number 0, and including all the numbers you can get by negating each of these numbers. So we can start off from negative infinity and work our way down to, let's say, negative 3, then negative 2, negative 1, 0, positive 1, positive 2, positive 3, and then going up to positive infinity. So 2 infinite sets so far of um, of different elements where the natural numbers just has the positive integers and the integer set contains the negatives and the number 0. Okay, the fourth set will be the set of rational numbers, which gets denoted by a bold-faced Q. And we're going to use the notation we learned in the last video, which is going to be the point notation. So the natural number set can be denoted by the set containing the ordered pair AB, or the point AB, such that it contains all the elements that we can create by taking A and dividing it by B. So it creates this ratio, but we need a few descriptive touches on A and B. So we want A and B to be integers. So here's that in symbol again. So we're declaring that A and B must be in the integer set. So A and B can only be the numbers in this set. And we also must have that B not equal 0, right? We don't want B to equal this because if we're dividing by 0, then this may be undefined or indeterminate if A is 0. And we don't want that. Okay, so what kind of elements are in the rational number set? Well, pick any two integers in the integer set. Let's say the number 2 for A and the number 3 for B. So if I pick the ordered pair 2, 3, where 2 is my A and 3 is my B, then I know the element 2 over 3 is going to be an element of the rational numbers. Or if I pick the numbers 6 and 12, I know that 6 over 12, which simplifies to 1/2, is also going to be in the natural number set. We will always be simplifying if we can. And that final simplified ratio is the element that is going to be in the rational number set. If I pick the number or the point 3 comma 1, then 3 over 1, which is just 3, is also going to be in the rational number set. Okay. And the final set we should talk about is the real number set. So real numbers. And the real numbers includes every number that is in the rational number set in addition to all the irrational numbers. And the irrational numbers are basically all the numbers that cannot be written as a ratio of two integers. So for example, if I have the number square root of 2, I cannot rewrite this number as a ratio of two integers a over b because, and we can actually prove this, but we won't, but it can't be. We could write it as a general ratio of square root of 2 over 1, but square root of 2 itself is not a rational number. So this is not a rational number in general. And there are many more irrational numbers like pi or the other square root of 3, the number e, and many, many more. So that's what the real number set is. It's all the numbers in the rational set in addition to all the irrational numbers. And the way we'll define this is simply as all the points x such that x is between negative infinity and infinity. So all the numbers that you can think of between negative infinity and infinity, which includes rational and irrational. The final set of numbers I want to mention quickly is going to be the set of complex numbers. And the set of complex numbers gets denoted by a bold-faced C, which is going to be the set of all points A, B, such that A plus BI is going to be in this set, where I, if you've gone over imaginary numbers, is the imaginary unit where I equals square root of -1. And A and B are in the real number set. So that's what the complex number set is. And we won't really be using it at all. Maybe we'll mention it once further down the road if we're dealing with the characteristic function, but it's just good to enumerate all the sets that we may come across, so I'll include it just in case.